Hey guys, welcome back. We got day 2. We're starting chapter 1 in the Burge book. All right, so chapter 1, these are the learning objectives. All right, and so today I want you to think about chemistry. When you think about chemistry, what do you think about? All right, that's the whole premise. Okay, what is chemistry? All right, and you guys might have an idea, like if you had a box. All right, and what goes in this box of what you think chemistry is? Okay, reactions, right, or whatnot. If we were in person, I would ask you this, and you can give me some feedback. What is chemistry? And so your book gives you quick definition is the study of matter and the changes it undergoes, right? And one of the things with chemistry is we want to be able to predict behavior. That's a big thing. We like to predict behavior. All right. You want to know, like if you want to make a fire, you don't get wet logs. You want to get dry logs, right? Because wet logs, can they burn? Yes, but will they start a fire easily? No. Right? We know if you're going to store electronic devices, you don't store them in water. Okay, so there's things that you know about, behaviors and reactions and whatnot, and that's what we want to do. We want to expand on that. So the first thing your book dives into is the scientific method. All right? And the scientific method is a systematic way to approach things. All right, it's very methodical. All right, method, right, and it's not quick. It's not glorious. It's not like it is in the movies, but that's what it is. And so you have an observation. All right, we have an observation, something. All right, I'm going to use my middle guy as we did the scientific method. Right. We would notice that my middle guy, he would just be irrational at times. Just all of a sudden, out of the blue, boom, crazy. Everything would bother him, and they're little toddlers, tears and outbursts, and it was just crazy, right? He would just be fine, going along, playing, doing whatever, and then all of a sudden, man, crazy, okay? So then what could be doing this? Well, he's not being made fun of. He's not being picked on. We're not being mean to him. We didn't leave him someplace at a playground or anything like that. And so my wife and I decided, you know what? It might be, right? Our hypothesis could be that he's hungry. All right? And now it's more than just a guess. Okay, we didn't just guess that he was hungry. This little boy likes to eat carbohydrates more than proteins and fats. He loves carbohydrates. He'll eat other things, but carbohydrates are his favorite. And so our hypothesis, I bet you he's got low blood sugar, and that's his response. Kind of like the Snickers commercials of the diva, right? So when we experimented on this, we knew, okay, so if he ate lunch at 11:30, right, 3 hours later, he needs to have a snack. And we're going to make him eat a snack. Right? And the guy's skinny, right? The guy is, he's still skinny. He's almost going to be 11 years old at the time of this recording. And he can fit in size 8 waist. He is a skinny kid. And he's not the tallest or the bigger, but he's a skinny little kid. Right? And so we experiment that. And the theory is when he does have the snack, he's good to go. Right? He's good to go. Right? Doesn't have any of those outbursts. He's fine. Right? And it's even further, right? We even, the model, that's where our model is good, and we still test it years later. And if he hasn't eaten and it's dinner time, he'll be crazy right before dinner, and then he starts eating, and all of a sudden he's a different person. And so that was our scientific method with him. All right? And so the scientific method is a great way to do things like this. All right? So that is chemistry. Now, in chemistry, it's different because we're dealing with stuff that's big and small. But a lot of things we're talking about particles, like the matter and particles that we can't see, right? And so this is what leads us into measuring. We need to measure things, okay? We need to measure. What do we need to measure? All sorts of things, all right? And so a big thing in chemistry is the difference between measuring something and counting, all right? And we'll get to that. So let's talk about the measurements, all right? We have mass. Mass. So when you think about mass, what is mass? Right? It's the amount of matter. right? A lot of times we use weight. Well, on Earth, weight, and mass are the same because that's how we have it defined. But kilograms is the name of mass, and those do not change. If you go from your mass on here is on any other planet, the moon, whatnot, your weight changes because weight's due to gravity. And that symbol is kg. So that would be mass, how much mass, all right? Another one we have would be length or distance. And think about like space between or the space between or how long, space, long, right, distance between 2 points, right? And that would be a meter. Right now, we're used to feet and inches. So if you ask me how tall I am, or actually your height, right? It's feet, inches, right? A lot of the rest of the world they'll use centimeters, which is the prefix, which we'll get to in a second, right? And part of a meter. I'm 1 point whatever meters tall, or 170 centimeters tall, 190 centimeters tall, or whatever it happens to be. All right, another one, time. Think duration. And our SI unit is, second. All right, seconds. So again, this is the SI system, System International. So this is universal throughout the world, which is really convenient. Then we have temperature. Which is a measure of thermal energy. And that's the Kelvin, capital K. We have volume, that is like how much space. And that would be the liter, capital L. Another one we have would be the amount of substance. All right, think particles, moles. You may or may not want that. It's not the animal that I don't like in my backyard, but it's a counting unit we'll get to. Another one we have is electric current. Right, and this would be amperes, which is an A. And there's one more, luminous intensity, candelas. And I always mix up candelas and lumens. One has to do with the total amount. One has to do with like a point or something like that. And we don't use it, so we're not going to go there. So these are the basic units. So let's take a look at this. A kilogram. What is a kilogram? Well, if you have a liter of water in a bottle, like a Nalgene bottle with a liter, you take a little bit out because the bottle weighs a little bit. That would be a kilogram. Meter is a little over 3 feet, right? That's the distance. You guys know seconds. Kelvin is the same size as Celsius. We'll get to, right? So a liter is right like the volume, right? And so we're going to go there now. There are some derived units, and it's very important to know these derived units because the units do matter. Because what you're measuring matters. It may seem trivial, but it does really matter what we're measuring, okay? And we don't want to mix up what we're measuring. So, derived units. Velocity is the first one. We're going to use speed. Now, there's a difference between velocity and speed, right? You take physics, there's a big difference. We're not going to care about direction. We're just going to use speed, okay? And speed is the change in position over the change in time, or length over time, which are meters per second. We're not used to meters per second. We're used to miles an hour, but meters per second, that's the SI unit of speed or velocity. Then we have acceleration, which is the change in velocity over the change in time, which is meters per second divided by seconds, or meters per second squared. That's acceleration, your change in speed over time, right? The next one is force. Force. So force would be mass multiplied by acceleration, which would be kilogram is mass times meter over second squared, which is also a capital N for Newton. And that's Newton's second law. Right? That's a big one in physics class if you take physics. So you got Newton. And so what is that? Right? So if you have, again, go back to that 1 liter Nalgene bottle, if you have one of those, right? And if you put enough force on that Nalgene bottle to make it to move, and go by the base, right? Yeah, there's friction and all that stuff, but just get a rough idea, that's a Newton. Okay? It's not a lot of force. It's definitely not a lot of force. Then we have work, and I'm going to put and energy. But we're going to look at work this is work. Energy is not necessarily organized motion, but work and energy. And we're going to say that happens to be force. I'll underline work here. Force times distance, which is a kilogram times a meter over a second squared multiplied by a meter, or a kilogram meter squared per second squared, which is a Newton meter, which is a capital J for joule. So if you take your Nalgene bottle, your kilogram, or a kilogram of anything, you just had a kilogram, right? And you move that a distance of a meter, that's a joule. So that would be what a joule is. All right. Again, these are not huge units of energy, but that's the energy. That's what you had to exert to move that kilogram a meter. All right. The next one. All right. All right. Before we get to the next one, I like to always pause here and talk about exercise, because if you're a runner or you're a walker, the work to walk a mile or run a mile is the same as long as you're not changing speed, right? If you're changing, right, so work would be mass times acceleration times distance, right? So if you're changing your acceleration, you're speeding up and slowing down, then that's different, okay? But if you're keeping your acceleration the same, so if you're on a treadmill, let's say, and you both are there, you and a friend, and one of you is going at walking pace and one of you going at running pace, the calorie count on the treadmill, if you guys had the same weight, would be the same at the time limit, not necessarily the mile limit, all right? So it takes as much energy to walk a mile as it does run a mile, as long as you're not, again, playing with the acceleration, right? And so how is that possible? Because your mass isn't changing, and as long as your acceleration is not changing, so especially on a treadmill, work energy is the same. The difference would be power. Power, which is work or energy divided by time. All right? So work or energy would be kilogram meter squared second squared divided by seconds, or kilogram meter squared per seconds cubed, which is a joule per second, or a capital W for watt. So watts are energy per time, or work per time. So it's a lot more powerful to run a mile than it is to walk a mile, which is kind of neat. All right. Now, there's two more now that are not really, like, keep building. One of them is pressure. We've heard of this. Pressure. What is pressure? Well, pressure is force divided by area, which all that is would be a kilogram right? Meter per second squared divided by meter squared, or kilogram meter second squared. Or sometimes you'll see it written as newtons per meter squared, which is a PA for Pascal. Now, we don't use pascals a lot. We can, but we don't use it a lot. We do 101,325 pascals is 1 atmosphere. And so when we get to the using pressure, we will use that. And the last one is frequency. Frequency, and that happens to be 1 over time. All right, and so my county is a coastal county of North Carolina, and so Coastal Carolina Community College is located in Onslow County, which is on a coastal county of near the Atlantic Ocean, and there is a marine forecast, not the military base that we have, but the actual out in the ocean, and that marine forecast gives you the wave height and the period of the wave, which is how long the wave is, right? The frequency is the inverse of that, right? Which is how many waves per second, all right? And so we want to know what the frequency is, right? Which is 1 over seconds, or Hz for hertz. So those are our fundamental units and our derived units. So we know what the units are. So, when somebody says a joule or a newton, what is that? Well, it's broken down into what they actually are. And that's very, very important. All right. And we'll stop there. See you next time.